Hello everyone, welcome back to the fast track revision series of UGC NET Electronic Science. Right, so in this video we are going to learn about extrinsic semiconductors. Okay, extrinsic semiconductors. If you are first time to my channel, please consider subscribing and don't forget to hit the bell icon to get video notifications from my channel. Right, so intrinsic semiconductors already we have discussed in my previous video. So in intrinsic semiconductors, what is the disadvantage is to increase the conductivity, that is to increase the flow of current. So the only solution which we have is to increase the temperature, which is not acceptable solution. Okay, so to increase the conductivity we are going for extrinsic semiconductor, and extrinsic semiconductor is also called impure semiconductor. Okay, so we are going for a process called doping. So doping is the process of adding impurities. Okay, so adding impurities to pure semiconductor is called as doping. Okay, so as doping increases, as you increase the doping, you add on impurities. If you add on impurities, then conductivity always increases. Okay, so if you have more doping, then conductivity is more. If you have less doping, conductivity is less in the case of extrinsic semiconductor. Anyhow, we don't have any process of doping in the case of intrinsic semiconductor. Okay, so there are two types of extrinsic semiconductor. One is p-type and second is n-type. So I am writing in the form of a table. Right, so first difference is the type of doping, that is which type of impurities you are adding. The first difference exists. So for p-type, group 3 elements are added. That is, they are having 3 valence shell electrons. 3 valence shell electrons. And in n-type, we are doping with group 5 elements. Okay, so this is the first point in this. Group 5 elements, that is, they are having 5 valence shell electrons. So examples of group 5 elements are phosphorus, arsenic, antimony, and bismuth. Okay, so these are the widely used. And for group 3 elements, boron, aluminium, gallium, and indium. Boron, aluminium, gallium, and indium. Okay, so these are the types of impurities which we are going to add. Right, second, so when you are adding, so these are the electrons which I am showing here. Suppose I am representing with A and B. So there is another energy level which I have drawn here. So this is the energy band diagram of n-type semiconductor. Okay, so similarly we'll have the p-type semiconductor. Right, so when you are adding group 5 elements, so group 5 elements will have 5 valence electrons. So 4 valence electrons are involved in bonding, covalent bonding. 4 valence electrons are involved in covalent bonding with 4 adjacent atoms of semiconductor. So 1 valence electrons is always free. 1 valence electron is not free, but it is bounded to that group, bounded to that impurity. Right, so they are not involved in covalent bonding, but still they are bounded to impurity atom. Right, so they are bonded to impurity atom. So this bonding, which is bounded to impurity atom, we are going to show with another energy level which is called as donor energy level. Donor energy level. Okay, so the 1 valence electron is there. So why it is called as donor energy level? Because an electron. So in p type the impurity is called as acceptor impurity. This is one of the difference, acceptor impurity. In n type it is called as donor impurity. Okay, so why it is called donor impurity? Because it is having one electron in excess. In the case of n type, you are adding fifth group element, so four elements are involved in bonding, and fifth element is bounded to the impurity atom. So by donating one electron, by donating some extra electron, which is fifth electron, it is involved in current conduction. That is why it is called as, that impurity is called as donor impurity. In group 3 already there is one electron which is less in number, because adjacent atoms will have four electrons which have to be involved in bonding, but group 3 elements has only 3 valential electron. So by accepting electron, by accepting one electron, right, so this p-type semiconductor is involved in current conduction. That is why the impurity is called as acceptor impurity. Okay, hope you understand. So the energy level here is called as acceptor energy level, acceptor energy level. So here it is called as donor energy level, donor energy level, represented by ED, and here it is represented by EA. Okay, so this is the process. So this is called as donor energy level. When you apply some external force, on this semiconductor, what will happen? So covalent bonds will get broken and electron will jumps from valence band to conduction band, leaving a hole here. Similarly, this electron also will jump from valence band to conduction band, right? So due to this external energy which is applied, the fifth electron also will jumps from donor energy level to conduction band. So from here to here, no hole will be there here, because it is not leaving, or what is hole? Non-existence of electron in covalent bond. So all these electrons are not involved in covalent bond, so they are the fifth electron, fifth valence electron in the which is bounded to impurity atom, which is due to impurity atom. So they are not involved in covalent bonding. So when they jump from donor energy level, so from donor energy level to conduction band, when it jumps from donor energy level to conduction band, so no hole is left over. So if you observe here, when an external force is applied, so number of holes formed here in this example, up to this example we'll consider, so number of holes formed here is 2 and number of electrons formed here is 4. This is because there are excess of electrons due to impurity atom. There are excess of electrons due to impurity atom. So that is why the third point here is, since the number of electrons are more, number of free electrons are more, so in the case of n-type semiconductor, electrons are majority carriers. Electrons are majority carriers and holes are minority carriers. Exactly opposite here. So holes are majority carriers and electrons are minority carriers. That is, n is greater than p and here p is greater than n. Okay, understood? So why it is called as majority carriers? The explanation is important, right? So you have to learn in that way. Right, so this process of exciting the electron from donor energy level into conduction band is called as impurity ionization. This process is called as impurity ionization, and this process is called as band to band transition. Band to band transition. So in extrinsic semiconductor, current conduction is due to two processes. One is band to band transition. Okay, so this band to band transition is common in intrinsic and extrinsic semiconductors. So it is there in intrinsic semiconductor also. But impurity ionization process, impurity ionization process is there only in the case of extrinsic semiconductors. So why this process is called impurity ionization? By donating an electron, the impurity atom is becoming positive ion. This is very, very important point. So impurity atom will become positive ion in the case of n-type semiconductor. So here the impurity atom will accept an electron. So that is why it is called as acceptor impurity. So impurity atom will, when you accept some negatively charged particle, so it will become negative ion. Okay, so that process is called as impurity ionization. Impurity atom is getting ionized by donating electron or by accepting electron in the case of n-type and p-type respectively. So due to this process of impurity ionization, extrinsic semiconductors will give you more current. So extrinsic semiconductor will gives you more current when compared to intrinsic semiconductor. So this is very important point. Okay, so this is generalized point, so I have not written here in the differences. Okay, so always impurity ionization, due to the process of impurity ionization, always extrinsic semiconductor will gives you more current when compared to intrinsic semiconductor. Okay, so these are the main points which you have to remember. So holes and total current conduction is always, so I is always equal to IN plus IP. IN plus IP in the case of both p-type and n-type. Since there are more concentrations here, so IP is greater than IN here and IN is greater than IP here. Okay, so this is the fifth difference. Okay, so that is the points which you have to remember. So there are some more points which you have to remember is all intrinsic and extrinsic semiconductors are electrically neutral. Electrically neutral. There is no charge, right? So there is no charge present in intrinsic and extrinsic semiconductor, are all electrically neutral. Next very important point is at 0 degrees Kelvin. At 0 degrees Kelvin, all intrinsic and extrinsic semiconductor acts as insulators. Okay, so all intrinsic and extrinsic semiconductors will act as insulators. Okay, so all these are very, very important points which you have to remember for in the case of intrinsic and extrinsic semiconductors. Okay.